All right, welcome to Lesson 5, Gravitational and Normal Forces. In this video, I'll be doing the second example of the topic. But before we get on to that, I just want to briefly discuss about what normal forces are. So, the normal force is, the book says, a force that comes from pressing two surfaces together. We kind of saw the normal force at play in the last topic, when we had the chains of boxes pushing on one another. The normal force is really just the application of Newton's third law, right? When an object pushes on a surface, that surface that you're pushing on pushes back. If we were pushing on a wall, the force of resistance that the wall gives us is that normal force. Likewise, if we were sliding a block down the road, the block would be resisting us, and we could feel that in our hand, that resistance of us having to put in effort. Right? That is the normal force. 3 examples in the book are demonstrating how normal force is always perpendicular to the surface. So if we're standing on flat ground, sure, it's going to be straight up. If we're on a hill, the normal force is going to be at whatever angle or perpendicular to whatever angle that hill is. We're going to be dealing with that really soon when we get into friction. And the last one, we are dealing with like a spinny ride at a town fair. Whereas that thing spins around, the centripetal force is going to push you into the wall, and the sensation of being pushed back inward, or the feeling on your back, is going to be the normal force pushing straight inward. Okay. Anyways, jumping into this example now. The example has a 700 Newton person on an elevator, which I've sketched here. And the elevator is accelerating downward at 5.8 meters per second squared. If this person is on a weight scale, what is the reading while they are moving downwards at this acceleration? All right, so I think what we need to start with is, really we need to start with our free body diagram here. Let's do it on our person, and our person, I've put their weight up here, but really I think the better place to put this is drawing it on. Right, so this person, their weight is their force of gravity, is pulling them downward, and we can call this our Fg, which is equal to 700 newtons. Now, upwards, the ground is Newton's third law, pushing up on them just as hard as they are pushing down on the ground, assuming this thing isn't moving yet, but we'll get to that very shortly. Okay, so upward on this person, we're going to have the normal force of the floor on the person. All right. Now, before we get too crazy here, it's great that they gave us the weight of the person, but I don't think we can really move on until we find the mass of this person. The reason I say that is because if we want to find this unknown force, we're going to be using our same Fnet formulas. We're still going to be using Fnet is equal to mass times acceleration, and Fnet is equal to the sum of our forces. So force normal plus force of gravity. Okay, we are ultimately looking for force normal. We have force of gravity, but we can't find Fnet without mass. So step 1, let's find mass. What color should I do this in? Why not blue? Okay, well, we have our gravity, force of gravity formula, right? Force of gravity, which is weight. This is the weight, is equal to m little g. We know what little g is. It's constant here on Earth, and we're assuming that this is probably happening on Earth. As far as I know, it's the only place elevators exist. And we are going to solve for the mass of this person. So mass is equal to force of gravity over little g. Plug some numbers in there. 700 newtons divided by 9.81 meters per second squared, and we end up getting a mass of this person equaling 71.36 kilos. Awesome. Now we have mass. We can find force net on this person. We know how quickly the acceleration is going on here, right? The acceleration is downward. We know the mass of this person, so we can figure out their net force. So let's do that. Switching to magenta for this. F net is equal to the mass times acceleration. So we have 71.36 kilos. And we're going to multiply by the acceleration of the elevator or everybody in it. So 5.80 meters per second squared. So F net here should equal 413.888 newtons. And this acceleration was downward, so I should probably put this as downward as well. Really, to be honest, I should have made this negative. This would have turned out to be negative, and then we could have had this would have been negative upward, and then we would have said it's downward. But as long as we realize that this 5.80 meters per second squared is the acceleration downward, and we label the direction here, I think we're safe. Okay. Now, what else do we have? Well, we found force net. So now we have force net, force of gravity. We just need to find the remaining normal force acting on this person. So, to red, and we're done. F net is equal to the sum of all the forces. There's only two here. Whoops. Force normal plus force of gravity. Our net force is equal to negative 413.888 newtons plus force normal, which we don't have yet, force of gravity, plus negative 700 newtons. Right? 700 newtons downward, because gravity is downward, and downward is our negative direction. So really we're going to be subtracting 700 newtons. And if we work this out, one sec, why did I put a plus here? Just a writing mistake. Okay, this is that equals that plus that. That equals that plus that. Okay. Do some rearranging, plug a couple things into our calculator, and we learn pretty quick that the normal force works out to 286 newtons. It's a positive value, so we can say upward. And that is how we determine the normal force in an elevator. This person, normally weighing 700 newtons, feels much lighter, 286 newtons, when the elevator is accelerating downward.